Hey guys, this is Yuichi Greywright from Salutary, Spade Science, and this is the Part B video of the first lesson. We're going to be going over Newton's second law of motion. Remember? Do you remember from this, and you would remember from this equation, F equals ma. Okay? This is the equation that summarizes the second law. Okay? So now let's put it to use. Let's talk about this. Okay? So one thing. So first, let's talk about a ball. Let's say that we have a ball, okay? And then the ball is moving at a constant velocity. Mostly in math we would use a c for constant, but in physics we use k most of the time for constant, because c is the speed of light. Yeah, but anyway, this ball is moving at a constant rate, and it has a mass is equal to 60, and its velocity, or velocity isn't good, it's speed is equal to 20 miles per hour. Okay? And then we have, but then we notice that, you know, it's moving at a constant rate. So the mph, miles per hour, the speed is not going to change at all. So basically, we just represent that, and acceleration equals change in speed. Okay? And this can be represented, see, this is delta, for those of you who don't know. Yeah, this just, you know, represents change. Okay? So, and this is equal to the initial speed minus the secondary speed, the speed that is not now, the current speed. Okay, and that's acceleration. So now we want to know how much force is the ball exerting on space-time, and space-time exerting on the ball, as we know from Newton's third law, and we're going to get into that in the next video. So, how do we solve for this? Well, this is actually really simple. If it's ma, a is equal to 0, it's not accelerating at all, 60 multiplied by 0, unsurprisingly, equals 0. There is no force acting upon the ball here, and despite what most people would think, there isn't. Okay? So, a lot of people would probably be disagreeing with me because, you know, logic. Like, at first, it seems like this is not true. But when we get into physics a little bit more, especially into gravity, we're going to see this a lot more. And we're going to see, and it's just going to continuously prove this over and over and over again, okay? So let's talk about another thing. Let's say that's supposed to be a duck. That's a really bad duck. Okay, but let's say that there's a duck, and it's moving through space. It's disintegrating, which doesn't really make much sense. Let's just assume that this is some form of error that doesn't, I don't know. It wouldn't actually be disintegrating like this if there's no friction, or if there's no, if it's in a vacuum. Let's assume that this is in a vacuum. This isn't a very accurate drawing. But anyway, this duck is accelerating, I should say, at, let's say, 7 meters per second squared. And see, this squared, if meter, so now we're using meters per second. We did miles per hour before. Now we're doing meters per second, different units. So in this squared here, just, says that this guy's accelerating at 7 meters every second squared. He's accelerating. You can do the math stuff and solve it, okay? So now, let's say that this guy has a mass of 20 grams. Okay? I didn't add things over here. The units didn't really make much of a difference in the outcome. But, so let's say that this is 20 grams, okay? And we know that F is equal to MA. So how do we solve this? Force is equal to 20 times 7 meters per second squared, and this is supposed to be grams, and that is equal to 140. And the units are kind of weird. Well, this actually we would use a unit called newtons. Okay? Newtons, named after Isaac Newton, was I don't know, because he just was the kind of person to figure this out. Okay? So 140 newtons. That is our answer, and that is the force that the duck is exerting outwards, and that we know that space-time exerts on the duck. Okay? Well, I'm pretty sure it's newtons. I should probably know this. It is, I'm guessing. So, yeah, 140 newtons. That's how much pressure, or not pressure, but, force the duck is. Okay? So, I wonder, how long is this video so far? Oh. It's been 7 minutes already. So let's just do one more, problem. Okay? Now let's talk about light. Okay? This is gonna bug you guys, I think. I don't know, I'm not thinking that far ahead. So let's just say that this is a beam of light. Okay? The light is moving at a constant rate, the speed of light, c, and its mass is equal to 0. Huh? What?
What are you doing?
Stop, I'm
Want
doing
to do
this.
something with me and Brendan?
No, not right now. No, that's my little brother. He's being stupid. Yeah, so M is equal to 0. A is equal to 0. If F is equal to MA, M equals 0. 0 times 0 equals 0. So, yeah. Of course, this is actually wrong. Kinda. See, the thing is that in most, see, this is called Newtonian physics or classical mechanics. Or it's actually not called classical mechanics, but Newtonian physics, basically, when with all this stuff that I'm teaching you guys, the closer you get to the speed of light, the more inaccurate these things get. And I'm not going to get into that until we finish our unit on classical mechanics, and we're going to go into optics and relativity, which includes special relativity, which basically is Newtonian physics, except that it acknowledges that the speed that light has speed, and the closer you get to that, the slower time seems to run, and all these other effects. General relativity, which actually describes gravity with a lot more precision. I should probably not get into this stuff because I was going to surprise you. I guess not. And also, I'm going to get into I am going to get into optics and, mirrors and light and stuff. Okay? Yeah. So, this has been Yuichi Greywright from Salutary Spade Science. And, yeah. Like and favorite if you, enjoyed. And, subscribe to, get these videos as they come out. Comment. That's why we have a comment section. So you can comment on videos and stuff. Okay, so, yeah. This has been Yuichi Greywright, and I am signing